over the three fractions, resistance 1 plus resistance 2 plus resistance 3, 1 over those. That's fractions. Okay? Now, if the denominators are all the same, you can add fractions together. So that 12 ohms as a total resistance can also be expressed as 1 over the fraction 3 divided by the resistance value for each one of those resistances. Now we can simplify that expression just a little bit. The 12 ohms total resistance is equal to 1 divided by 3 over the individual resistances. Now we want to get rid of the division sign. All we have to do is flip-flop that fraction, as you know. So that total resistance is equal to 1 times the individual resistances divided by 3. And now we can begin to see that we can figure out the value of each individual resistance. And so that total resistance of 12 ohms is equal to R, that's the individual resistance of each resistor, divided by 3. Multiply each side by 3, and you find out the value of R is 36 ohms. The value of each one of those individual resistors is 36 ohms. All right, so what we did first of all is figured out the current for the entire circuit. Then we figured out the resistance, here current for the entire circuit, then the resistance for the entire circuit. Then we used the formula for parallel resistance, parallel circuits, and then we found out the value of R, which is each one of those resistances. You guys have got it made. You're doing fantastic. All right. What's the operating resistance, the next question says, of a 30-watt bulb in a 28-volt system? And the question is, what is the resistance? Well, first of all, let's figure out the current, and then we'll figure out the resistance. That makes it pretty easy. The current works out in a formula like this. Here's the current is equal to the power in watts divided by the volts. Power in watts is 30, volts is 28, the current is 1.07 amps. Once we know the current, then we can figure out the resistance with Ohm's law. And resistance equals the volts divided by the amps. The volts was 28, the amps is 1.07, and the resistance is 26.17. And that is the answer to that question. Let's take a look at another question involving parallel circuits. The FAA is trying to make your life complicated with these parallel circuits, and they're doing it. Let's take a look at the question they're going to ask. First of all, they say that you have a 24-volt source, and that's the voltage that's required to furnish 48 watts to a parallel circuit, and this circuit contains 2 resistors of equal value. Now the question is, what is the value of each resistor? Oh my God. We can figure it out, never fear. Let's take a look at another bit of information they give you that's extremely valuable. They tell you that the total resistance in this circuit, they give you this formula, the total resistance is equal to the voltage squared divided by the power. So they give you that formula. That's a tremendous help. So now all we have to do is plug in some numbers. We know that the total resistance is equal to voltage squared divided by power, and the voltage we know was 24, and the power was 48 watts. So you take the 24 times 24 divided by 48, you do that with your electronic calculator, and you're going to get 12 ohms. And so right now we know the total resistance in that circuit is 12 ohms. Now we talked about earlier the formula for the resistance when they're in parallel in a circuit, and it's 1 divided by 1 over R plus 1 over R. And in this case these resistors are equal to each other, so this value of R is the same in each case. So that 12 ohms resistance, that's that total resistance, is equal to 1 divided by, and you can factor out 1 over R here, and it's 1 plus 1 times the quantity, 1 divided by R, and it's the same as 1 plus 1, that quantity, divided by R. So we factored out that 1 divided by R, and it's 1 plus 1, that quantity, times 1 divided by R, which is the same as anything divided by R over R. And now we have the total resistance, that was 12 ohms, is equal to 1 over, and this is 1 plus 1, that comes out to 2. 2 divided by R. So that's all there is to it. And so the total resistance is 1 divided by 2 divided by R. Well, to multiply, all we have to do is flip this. So it's total resistance at 12 ohms is equal to 1 times R divided by 2. Okay, 1 times both of these means the total resistance is equal to R divided by 2. That's all there is to it. And the total resistance was 12 ohms, and so 12 equals R divided by 2. Multiply both sides by 2, and R comes out to 24 ohms. The value of each resistor comes out to exactly 24 ohms. Well, let's do it a little bit more complicated. Question is, how much power must a 24-volt generator furnish to a system with the following loads? And this is the following loads right here. We have a 24-volt generator. You have one motor that's 75% efficient, and it's 1/5 horsepower. You have 3 position lights in the airplane. They're 20 watts each. You have one heating element that is 5 amps, and you have one anti-collision light that is 3 amps. How much power is required? Well, we have watts here, we have horsepower here, we have amps here. Let's convert this all into watts. First of all, let's figure out the motor. Now, there is something they give you that you absolutely have to have, and don't panic because you don't know this, because they tell you this. What they tell you is that 1 horsepower is 746 watts, and you do not need to memorize that. They tell you that when they give you the question. Now, this motor was only 75% efficient, so in order to get 1 horsepower, you actually have to have 746 watts divided by 0.75, or 75%. That would come out actually closer to about 1,000 watts. And we weren't actually looking for 1 horsepower in this case. We were looking for 1/5 horsepower. So what we'll do is we'll take 1/5 times 746 divided by 0.75, and you find out this motor requires 199 watts. Now, they told us also they had 3 position lights, and each one of those was 20 watts, so 3 times 20 is 60 watts. And they also told us we had a heating element, but they said the heating element was 5 amps, not watts. And so we need to convert that into watts, which is power. And so what you do is use this formula for power, and you take the current times the voltage, or the electromotive force, and that gives you the power in watts. So it was 5 amps times the 24 volts gives us 120 watts. All right, now let's take a look at the rest down there. The anti-collision light was 3 amps. And a 24-volt system, so we can do the same thing. 3 times 24 is 72 watts. And all we have to do is total those up. We had 199 for the motor. The position lights was 60 watts. The heating element was 120 watts. The anti-collision light was 72 watts. And the total of that is 451 watts. So if you know these formulas, you got it nailed. They're just asking you to be able to multiply volts times amps to get watts. And that's all we had to do in that particular case. Now, here's a question the FAA is going to ask you that I think is actually kind of fun. It involves 3 different types of electrical systems, and it says, which one of these do you think will require the most electrical power? Well, let's take a look at each of these 3 situations one at a time. In the first one here, you have 4 30-watt lamps, and they're arranged in a 12-volt parallel circuit. Now, they ask you about power, and what's the term you use to describe power? It's watts. So they've already told you you have 4 30-watt lamps, so the total power is going to be 4 times 30, or 120 watts right there, and that is deceptively simple, so the first circuit is 120 watts. Well, that's pretty easy. Let's do another one. Now you have a 24-volt anti-collision light circuit. It consists of 2 light assemblies which require 3 amps each during operation. Well, let's take a look at this. First of all, power, as you remember, is amps times volts. Well, we have 3 amps and 24 volts. So this is 3 times 24 in each circuit, and that's the power required in each circuit. It's the amps times the volts. And we have 2 of those circuits, so to figure out the power here, 2 times 3 times 24, that's the power in each circuit, equals 144 watts. So that's a little bit more. That's 144 watts. So let's take a look at the third situation they're going to ask you about. Here you have a motor that produces 1/5 horsepower. It's a 24-volt motor that's only 75% efficient, and they tell you that 1 horsepower is equal to 746 watts. That's a key bit of information you have to know, but they already told you that. So let's take a look at it. First of all, we have 1 horsepower is 746 watts,
but this motor is only 75% efficient. So to produce horsepower, it's 746 divided by 0.75. So that would give you 1 horsepower. But we're only talking about 1/5 horsepower, so we'll multiply that times 1/5. So the formula will be 1/5 times the power required for 1 horsepower, 746 watts for 1 horsepower, but it's only 75% efficient. And then you multiply that out and you get 199 watts. That's the one that requires the most power, and I think that's a fun question.
Now here's another question involving power they're going to ask you about on the test. They're going to say, let's assume that you have a 12-volt electric motor and that it has a 1,000 watt input and a 1 horsepower output. So you can see it's pretty efficient. Now let's assume that you had a 24-volt motor with 1 horsepower output that had the same efficiency ratio. The question is, how many watts would be required? And the answer is the same 1,000 watts. If it has the same efficiency ratio, watts to horsepower, it's going to be the same down here, still 1,000 watts. And whether it's 12 volt or 24 volt doesn't make any difference. Now let me ask you a question. Do you think that even in the most remote stretches of your imagination that the FAA could ever be deceptive? You bet they can, and here is a case in point. They have a question like this, they give you this information. They tell you that you have a 1 horsepower, 24 volt DC electric motor, and that this electric motor is 80% efficient, and it requires 932.5 watts to produce that 1 horsepower. They give you that information, then they ask you this question. They're going to ask you, how much power will a 1 horsepower, 12 volt DC electric motor require if it's 75% efficient? How much horsepower or watts will be required to produce that 1 horsepower? And they also tell you that 1 horsepower equals 746 watts. Now you might look at this and say, hold it, wait a minute. What does this top part have to do with this question? I've got the information I need right here, don't I? And the answer is, this top part had absolutely nothing to do with the question. They just threw that in there to confuse you. It works, doesn't it? Well, now, if this engine, this motor, were 100% efficient, it would take 746 watts to produce this 1 horsepower. But in this particular case, we're told it's 75% efficient. So all you have to do is take that 746 watts divided by 0.75, and you're going to find out that it's going to take about 1,000 watts to produce 1 horsepower, actually 994.7 watts, and you have produced 1 horsepower, and that is a case of being very tricky. Let's do another one. This time they're going to say you have a 14 ohm resistor to be installed in a series circuit carrying 0.05 amps. Now the question is, what is the power required to be dissipated by that resistor? All right, let's take a look at it. First of all, we want to know how many volts are in the circuit before we can multiply volts times amps to get watts. All right, to find out how many volts are in the circuit, you use this formula. Volts is electromotive force equals the current, which is I, times the resistance. The current was 0.05 amps, and the resistance was 14 ohms, and you multiply that out, and we have 0.7 volts. Now we have the information to find out power, and so you take the volts, which was 0.7, and multiply it times the current, which is 0.05, and 0.05 times 0.7 equals 0.035 watts. And that's 35,000th of a watt. Another way to express that is 35 milliwatts, because 1 milliwatt is 1,000th of a watt. All right, let's do another one. This time, let's take a look at Figure 8, Appendix 2, the FAA's book, and they give you a circuit like this, and they say, how much power is being furnished to this circuit? Well, once again, first of all, you have to find the voltage before you can multiply the volts times the amps. Well, let's call this a generator. Let's call this a 23 amp meter here. It's an ammeter, and it's measuring 23 amps and a resistance of 5 ohms. And so we know the amps and we know the resistance. So now let's take a look at what we need to do to find volts. Well, if you remember the formula, it's very simple. Volts equals the amps times the resistance. And we have 23 amps and resistance of 5 ohms. It's 115 volts when you multiply that out. To find the power, you multiply the current times the voltage, and the current was 23 amps, the voltage was 115. Multiply that out, and it's 2,645 watts. All right, it's getting simpler and simpler and simpler, isn't it? Let's do another one. Let's assume that you have a 30-volt, 1/2 horsepower motor that is 85% efficiency. The question is, how many amps will it draw? Well, first of all, let's find out how many watts this motor is, and then we can figure out how many amps it is. All right, to find out how many watts, we have a 1/2 horsepower. They will tell you, once again, that 1 horsepower is 746 watts. You do not need to memorize that. Don't worry about that. And it's 85% efficient, so to produce 1 horsepower at 85% efficiency, it would be 746 divided by 0.85. We only want to produce 1/2 horsepower, so we multiply that times 1/2. So it's 1/2 times 746 divided by 0.85, and it's 438.8 watts for this motor. But hold the phone, they asked us for amps, and the formula for amps is the current equals the power in watts divided by the electromotive force in volts, and the power is 438.8 divided by the 30 volts, and so the current is 14.6 amps, and that's the answer to that question. Now, before we wrap up DC current, I want to cover those formulas that you need to have in your mind when you walk into that test room. Let's take a look at them. First of all, if you remember, you need to know Ohm's law. And Ohm's law is current in amps is equal to electromotive force in volts divided by resistance in ohms. Now, if you know that, you can get the other two in Ohm's law if you're good with algebra. But the other two are that the electromotive force in volts is equal to the current in amps times the resistance in ohms, and the resistance in ohms is equal to the electromotive force in volts divided by the current in amps. You need to know those three. If you got algebra nailed, then all you have to do is know the first one and you can figure out the other two. Now let's take a look at the formulas for resistance. First of all, resistance in series. To find the total resistance in the circuit, just add up the individual resistances, however many there are. Resistances in parallel. To find the total resistance, you use this formula. It's 1 divided by these fractions. 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. If you know those two resistance formulas, you've got that taken care of. And finally, let's take a look at the formula for power. Power is equal to, and it's in watts by the way, equal to the current in amps times the electromotive force in volts. And the other formula for power, you can figure it out algebraically. If you know this one, you can figure this one out. But the other one is that the current in amps is equal to the power in watts divided by the electromotive force in volts. Now, if you've got everything that we've talked about, you have everything you need to know about DC current on the general exam. Now, let's see if you and I can figure out AC current or alternating current. Now, alternating current is different than direct current. Direct current goes only in one direction. Well, alternating current goes in one direction, then it reverses itself, goes the other direction. Then it reverses itself, goes the other direction. Then it reverses itself and goes the other direction. I think you get the idea. Alternating current periodically changes in direction and continuously changes in its magnitude. Now, if you look at it in a sine wave, you'd see what I'm talking about. Here's what it would look like in an oscilloscope. And this is a sine wave on an oscilloscope, and it describes or shows you what alternating current looks like. Now, here's the midpoint, and you have the alternating current first going one direction and very low intensity, and then it increases its intensity, and then it begins to level off, gets weaker, then changes direction, goes the other direction, gets stronger in intensity the other direction, weakens off, and so on, back and forth and back and forth. Now, they're going to ask you on the test, how would you describe alternating current? Here's how you define alternating current. It's current that periodically changes direction and continuously changes in magnitude. And that's a picture of what alternating current looks like right there. Now, there are three values regarding alternating current that should be considered. They're instantaneous, maximum, and effective. Let's take a look at them. First of all, the instantaneous value of alternating current is the value of the induced current or voltage flowing at any instant. And let's take a look at that in writing here. The instantaneous value is the value of voltage or current flowing at any instant. That's the instantaneous value. In other words, at any particular time, you can figure out what the value of the current is. That's the instantaneous value. The next thing we want to see in writing is the maximum value. And the maximum value is the largest instantaneous value. It's the peaks here. That's the maximum value, the largest instantaneous value. Finally, what's really important is the effective value. And the effective value is the direct current to produce an equal heating effect. In other words, if you're trying to heat up the circuit, how much current would you have to do in direct current to produce the same values as this particular alternating current? And that's the effective value. And by the way, unless somebody says otherwise, when they talk about the value, they're talking about an effective value. And as a rule, by the way, the effective value, would you think it would be more or less than the instantaneous value? And the answer is the effective value is less than the maximum instantaneous value, because the effective value is kind of an average. It's called a root mean squared, but it's really an average, and it's less than the peaks or the maximum instantaneous voltage. So the effective voltage would be less. Now, once again, unless otherwise specified, any values given will be effective values, unless somebody says otherwise. And that's either for current or voltage in an AC circuit, and that's what you assume is effective values. Let's talk about lines of force, because that's a concept that will be useful later on. Anytime you pass a current through a wire, you create a magnetic field around that wire, and that's called lines of magnetic force around that wire, and that's what we're talking about. And when you apply a voltage to put a current through a wire, first what happens is you create a magnetic field, and that actually delays the flow of current for just a little bit, and so the current doesn't flow for a while. Then when the magnetic field is created, the current flows. If you happen to apply alternating current, what happens is first you have a voltage applied in this direction. There's a little delay while the field is being created, and then when that voltage drops off, the current still flows for a while the field collapses. Then you apply a voltage in the other direction. There's a delay while the magnetic field gets created and so on. But you have a constantly collapsing and expanding magnetic field when you run alternating current through a wire. Now, if you want to intensify that magnetic field, you can do something very, very creative. What you can do is take that wire and wrap it into a coil, and you concentrate or intensify that magnetic field and get a much stronger magnetic field. If you want that magnetic field to be even stronger yet, what you can do is put an iron core in here, and that really concentrates the magnetic field. And in fact, one of the things you want to know is magnetic lines of force pass most readily through iron when compared, we'll say, with copper or aluminum, and therefore putting an iron core in here really concentrates the magnetic field. Now, another bit of information you might want to know is that if you took an electromagnet, let's assume you don't have any current through this wire right now, and you just take any kind of magnet for that matter, take a magnet and wave it by this wire. What you'll do is as you wave the magnet by this coil of wire, you'll create a current in that wire. Of course, that's the basis on which a generator works, and that's one way of creating a current, is just take a magnet and pass it by a wire, and you'll create a current in that wire. Now let's get a little more complicated. Let's have two coils of wire. Here we have a coil of wire with an iron core and another coil of wire with an iron core through it. In fact, we'll have the iron cores be connected, but these two coils of wire will not have connected electrically in any way at all. Now, let's assume that we put an alternating current in this coil of wire. What happens is we're going to create a magnetic field that keeps expanding and collapsing. Well, we said if you run a magnetic field past a coil of wire, you could create a current in that other coil of wire, and that's exactly what happens here. The expanding and collapsing field from this coil of wire creates a current in this coil of wire, even though they are not connected to each other electrically in any way. So transfer of electrical energy from one conductor to another without the aid of any kind of electrical connections between the two, that is called inductance. And this arrangement is called a transformer, where one coil creates a current in another coil over here, and the basis for transformer operation in the use of alternating current is what is known as mutual inductance. The magnetic field from one coil induces a current in the other, and that's called mutual inductance. So when you create a coil of wire in a circuit, you are creating what they call an inductor in the circuit. Now let's assume that we have an electrical circuit and we have a couple coils of wire. If you have one after the other, then you have more inductance inductance. In fact, when you put two inductors in a circuit, what happens is the total inductance is equal to the sum of the individual inductances. So now we have two coils, we have twice as much inductance. That means twice as much magnetic field, and in some conditions, twice as much impedance to the flow of current while that field is being created. Okay, now let's assume instead of having these in series, as this is, one after the other, you put these inductances in parallel with each other. Now you're going to find that there is less inductance totally. How much less inductance totally is there? Well, the total inductance is less than the lowest rated inductor of all of these. Of any one of these, is less than in any of them. This is putting inductances in parallel. Now, we said earlier, anytime you have inductance, a coil of wire, it tends to impede the flow of current. What's that called? Well, that is called inductive reactance. Let's take a look at the words for that. That's called inductive reactance, and it's measured in ohms. Why is it measured in ohms? Because it slows down the current, it impedes the flow of current just the way resistance does. And so it's called inductive reactance, and it's measured in the same unit that resistance is measured in a direct current, and it's called ohms. The unit is ohms. What is inductive reactance? Well, it's the inductive reactance is the opposition of the flow of a coil to the flow of alternating current. It tends to slow the current down. And remember, it does it it makes the current flow 90 degrees later than the voltage. Now let's take a look at a circuit here and see if we can make some sense out of it. Here we have a circuit, we'll say with a generator in it, and we have some resistance, some capacitance, and some inductance. And this is a typical circuit. We'll talk more about this later on. Now, as you increase the frequency of the current going through here, you change the rate at which these lines of force expand and contract around this inductance. And the higher the frequency of the current, the more inductive reactance there is. It tends to impede the flow of the current, and because it changes, expands, and collapses the magnetic field much more rapidly. So an increase in frequency will cause an increase in inductive reactance, and also the more the natural inductance, the more the coils of wire around there will change the inductive reactance. So an increase in inductance itself, and that is how many wires are wrapped around there, how tightly they're wrapped, whether or not you have a core in it, that will change the inductive reactance, and also the frequency of the alternating current changes the inductive reactance. So those are the two things that will change the inductive reactance to a current. Now, there's another thing installed in this current we haven't talked about here. We'll talk about that, and that is capacitance. Now, capacitance is basically two metal plates next to each other with an insulator, or a dielectric it's called, an insulator in between them. And what happens is, remember, this is current that tends to build up, and you build up a charge, and as the current flows, it charges one of these plates. So let's have the current coming through here, charging this plate. Now, if this were direct current, because there's an insulator between the two plates, the current would charge the plate and quit flowing because it couldn't get across this capacitor. But what happens is, with alternating current, the current tends to immediately charge the plate when it gets to a capacitor. In a static, all you're doing is putting a static electricity charge on the plate here. So if a static electricity charge on this big plate of metal, and it actually could be aluminum foil, two sheets of aluminum foil wrapped around each other with a dielectric or an insulating material between them. But anyway, you're charging this plate first, and if it's direct current, the current will quit flowing immediately. But if it's alternating current, the current tends to reverse in direction, and then what happens, the capacitor gives up its charge right away. And so then the current will flow back this way, charge the capacitor, then it gives up its charge when the current's going back. So this capacitor also tends to impede the flow of current. You can see that when you have direct current, the impedance is absolute. It just completely stops the current going through here. But if the alternating current has a frequency to it, as the frequency increases, this capacitor tends to impede the current less and less because it charges the plate and it gives up its charge. Charges the plate, gives up the charge. And the faster the current changes in frequency and direction, in other words, the faster the frequency of the current, the higher the frequency of the current, the less impedance is imposed by this capacitor here. And by the way, since the capacitor is almost like a short at first, it gives a place for the current to go, what happens is the current is about 90 degrees ahead of the voltage. Now impedance, remember that the current's about 90 degrees behind the voltage, and this is going to become important. So now what determines the amount that a capacitor can store? Well, let's take a look at it. It's directly proportional to the plate area and inversely proportional to the distance between the plates. If you have great big plates, it can store more electricity, and if you move those plates further apart, it can store less. So the closer the plates are together, the more it can store, and the bigger the plates are, the more it can store. Now, there is a maximum working voltage of a capacitor because the dielectric is only so strong. And so if you had too much voltage, it would just jump right across the capacitor and, of course, ruin the capacitor. So what they say is the working voltage of a capacitor should be at least 50% greater than the highest applied voltage you're ever really going to put on it. Otherwise, you could short out the capacitor and go right across it.
Now, sometimes in a circuit, including DC circuits, you'll see capacitors installed like